I spent the better part of 30 years building things the way I was taught: glue, screws, metal brackets, lag bolts. If a joint needed to carry weight, I threw hardware at it, and for the most part, it worked fine. Then, about 8 years ago, I got invited to watch a timber frame restoration on a 14th century tithe barn in southern England. The original oak frame had been standing for over 600 years. No nails, no metal anywhere in the structure. And when the restoration crew pulled one of the joints apart to inspect it, I just stood there staring. It was this interlocking puzzle of wood that had been carrying tens of thousands of pounds for centuries, and it fit together so precisely that you could barely slide a piece of paper into the seam. I asked one of the engineers on site how they would replicate that joint using modern methods, and he laughed. He said they had tried to model it with structural software, and the results didn't make sense. The wood was performing beyond what the calculations said it should. That conversation changed how I think about joinery. Today I'm going to walk you through 5 medieval timber joints that modern engineers genuinely struggle to explain, and show you why the old builders understood wood in ways we've mostly forgotten. Plus, stick around to the end because I'll share a marking technique from the medieval guild tradition that I now use on every single mortise I cut. Let's get into it. What we're looking at today comes from the golden age of European timber framing, roughly the 11th through the 15th century. These are the joints that built cathedral roofs, castle halls, tithe barns, and market houses across England, France, and the Germanic regions. And what makes them worth studying isn't just their beauty, it's their engineering. These medieval timber framers were not operating on guesswork. They trained through guild apprenticeships that lasted 7 years or more. They understood how green oak behaves as it seasons, how grain orientation affects shear strength, how gravity and compression can actually make a joint tighter over time instead of looser. They didn't have engineering software. They had something arguably more valuable. They had centuries of accumulated observation, passed down hand to hand in the workshop. Here's what I think most modern woodworkers miss about this tradition. We tend to look at old buildings and assume they survived by accident, or because the wood was somehow better back then. But the wood wasn't better. English oak is English oak. What was better was the joiner's understanding of how that wood would behave over decades and centuries. They designed joints that worked with the natural movement of the timber rather than fighting it. They oriented grain so that shrinkage would tighten a connection instead of opening it. They used geometry to create mechanical locks that actually gain strength under load. That's not primitive. That's brilliant. And when you start to see it, you can't unsee it. The first joint that absolutely floored me is called the tying joint, though today we'd classify it as a form of self-locking scarf joint. This was used to join two horizontal timbers end to end when you needed a beam longer than any single tree could provide. Cathedral roofs often spanned 40 feet or more, and finding a single oak timber that length was rarely practical. So they spliced them. But here's what makes the tying joint different from a simple scarf. The two mating faces aren't flat. They're cut with a series of interlocking steps and tapered wedging surfaces, usually at about a 2-degree angle, so that when the joint is driven together, it mechanically locks. The bearing surfaces are oriented so that any downward load, the weight of the roof, actually drives the tapered faces tighter against each other. The more weight you put on it, the stronger it gets. When modern engineers try to model this joint, they run into a problem. Finite element analysis assumes uniform material properties, but oak isn't uniform. The grain follows complex curves, and the medieval joiners selected timbers specifically so the grain would flow through the joint in a way that maximized shear resistance. One structural engineer I spoke with said the joint was performing at roughly 40% above what their models predicted, and they couldn't fully account for the difference. That 40% is the knowledge that lived in the hands of the builder and never made it into a textbook. The second joint I want to show you is the dragon beam lap, which is a form of splayed and tabled lap joint. You'll find this at the corners of medieval hall roofs, where a diagonal beam called the dragon beam meets the wall plate at a compound angle. This joint has to resist forces pulling in multiple directions simultaneously. Lateral thrust, vertical load, and rotational torque, all at once. The medieval solution was to cut a lap joint, with a broad, flat table on the bearing surface, then splay the shoulders at a precise angle, typically between 55 and 60 degrees, so that the geometry of the joint itself resists all three force vectors. There are no fasteners. The joint is held together by gravity and by the geometric relationship between the two timbers. I've seen reproduction versions of this joint tested to failure, and what happens is remarkable. The wood fibers themselves give out before the joint geometry fails. The engineering is stronger than the material. Think about that for a moment. The design of the connection exceeds the capacity of the oak itself. Modern steel brackets connecting the same two timbers at the same angle would typically require 3 or 4 through bolts and a custom fabricated plate. The medieval version uses nothing but wood meeting wood. By the way, if you are enjoying learning about these old world methods, I put together something I think you will really appreciate. It is called The Lost Workshop, and it is a complete guide to hand tool woodworking the way medieval craftsmen actually did it. 156 pages, 17 chapters, 33 illustrations, techniques like the ones we are covering today, and a whole lot more. You can grab your copy by scanning the QR code on screen, or just use the first link in the description. All right, let us keep going. The third joint is the one that I think truly baffles modern engineers the most, and that is the through-wedged dovetail mortise and tenon. You'll find this where a tie beam meets a wall post in major load-bearing frames, places like Westminster Hall in London, which was built in the 1390s and still stands today. The joint combines a dovetail profile, which resists withdrawal, with a mortise and tenon, which resists shear, and then adds hardwood wedges driven through the tenon from the outside. Here's the part that makes engineers uncomfortable. The wedges are driven at a slight angle, usually about 3 degrees off perpendicular, so that they create a clamping force that increases as the oak shrinks during seasoning. Green oak can shrink by as much as 1/16 of an inch per inch of width as it dries over the first few years. Instead of that shrinkage opening the joint, the angled wedges convert it into compression. The joint literally tightens itself over time. Modern structural analysis doesn't have a clean way to model a connection that changes its internal stress state over a period of years. It's a time-dependent, self-adjusting mechanism built entirely out of wood, and it was standard practice 600 years ago. The fourth joint is the hammer beam truss connection, and this one is pure architectural genius. A hammer beam truss allows you to span a massive open space without a tie beam running across the middle. Westminster Hall again is the most famous example, spanning nearly 68 feet with no central support. The secret is in how the hammer beam connects to the wall post and the arched brace beneath it. The connection uses a combination of a housed joint and a through tenon, with the bearing surfaces cut at precise angles that convert the outward thrust of the roof into a downward force on the wall. The geometry is so specific that changing the angle by even 2 degrees can dramatically alter the force distribution. Medieval master carpenters laid these out using full-scale drawings scratched onto the workshop floor, called tracing floors. They didn't calculate forces with equations. They drew them at full scale, tested the geometry physically, and refined it over generations. Modern engineers can analyze the completed structure and confirm that it works, but replicating the design process itself, that intuitive geometric reasoning, is something that doesn't translate easily into modern practice. The fifth joint is the diminished hunch with drawbore pin, and this is the one I've personally adopted more than any other. A diminished hunch is a small step cut on the top of a tenon that fills the gap left by the mortise groove, preventing the joint from twisting. On its own, that's clever but not extraordinary. What makes the medieval version special is the drawbore. The pinhole through the mortise is drilled slightly offset from the pinhole through the tenon, typically by about 1/8 of an inch. When you drive a tapered oak pin through both holes, that offset forces the tenon shoulder tight against the mortised timber. It creates a permanent clamping force with no glue and no metal. The pin itself is riven from straight-grained oak, so the fibers run continuously from end to end, giving it tremendous shear strength. A sawn dowel would have severed grain and could snap. A riven pin flexes and holds. I started using drawbore pins about 6 years ago on my own mortise and tenon work, and the difference in joint tightness is something you can feel immediately. The shoulder pulls up tight and stays tight. Let me share some patterns I've noticed over the years, things I used to do myself that this medieval tradition handles completely differently. The first pattern is reaching for metal fasteners by default. Most of us grab a bracket or a bolt anytime a joint needs real structural strength. But the medieval builders proved that wood-to-wood connections, when properly designed, can outperform metal in longevity and load distribution. Metal corrodes. Metal creates stress concentrations. Wood bearing on wood distributes force across a broad surface. The second pattern is ignoring grain orientation in joinery. I used to cut tenons without thinking much about which way the grain was running through the joint. Medieval framers selected and oriented every timber so that the grain would carry the load in the strongest possible direction. Once I started paying attention to that, my joints got noticeably stronger. The third pattern is treating wood movement as a problem to fight. We use joinery methods designed to restrict movement, and then we're surprised when something cracks or opens up. The medieval approach was to design joints that accommodate and even harness movement. Angled wedges, drawbore offsets, tapered surfaces. All of these convert wood movement into clamping force. The fourth pattern is relying on tight tolerances instead of mechanical advantage. We obsess over gap-free fits, which is fine, but a beautifully fitted joint with no mechanical lock is still just friction. The medieval joints use geometry, dovetails, wedges, tapers, and pins to create connections that physically cannot come apart under load. The good news is, once you see these patterns for what they are, you can start shifting your approach one project at a time. Now for that bonus tip I promised at the beginning. This comes from the medieval guild practice of using what's called a story stick for mortise layout, and it completely changed my accuracy. Instead of measuring each mortise individually with a tape or rule, the medieval joiners would take a straight, flat stick of oak about 3/4 of an inch wide and transfer all their layout marks onto it once. Every mortise location, every tenon shoulder, every pin center, all marked on one stick with a knife line. Then they'd hold that stick against every timber in the frame and transfer the marks directly. No accumulated measuring error. No misread numbers. Every joint in the entire structure referenced from one single master layout tool. I started doing this on a timber frame garden gate, and the accuracy was startling. Every joint pulled up tight on the first assembly, no trimming, no adjusting. And the whole layout took about a third of the time because I wasn't measuring anything twice. It's such a simple idea, but it's the kind of thing that separates a good project from a flawless one. One more thing before I let you go. I spent a long time gathering the best traditional woodworking methods I have come across, and I put them all into a book called The Lost Workshop. 17 chapters of medieval hand tool techniques that most modern woodworkers have never seen, with 33 illustrations and clear explanations you can actually follow in your shop. Scan the QR code on screen right now, or grab it from the first link in the description. I appreciate you watching, and if you want more of these deep dives, make sure to subscribe. I will see you in the next one.